We'll now look at the first type of redundancies in source text that compression methods can exploit, namely the character frequencies. As a first step, we'll look at general character encodings, and these are the simplest forms of encodings. As I said before, whenever we want to represent a string over some alphabet, we actually need to represent it in a computer in binary form. So we necessarily need some way of encoding the characters, of mapping the characters to binary strings. And that's what these encoding schemes do. They separately encode each source character. So they take each source character and map it with the function e to some code word. So some sequence of bits in the typical case. And we do this individually, independently for all the characters and just concatenate their codes. Usually we think of the source alphabet to be substantially bigger than the coded alphabet. So that means we need several bits per character, right? There's no way you can lie away that amount of information. Another bit of terminology, this bit string E of C will be called the code word for C. So that's the word that serves as a code for C in the coded text, if you want. And there's we can distinguish two fundamentally different types of such character encodings. They can either be fixed length or variable length. And as the name indicates, fixed length just means that the code words for all the characters in the alphabet are the same. The code words are of the same length. They have the same number of bits, and any other code is a variable length character encoding. There are well-known examples of fixed length codes. Here's one that I'm sure you've seen. This is the ASCII standard code for encoding, well, these 128 characters shown on the slide here. You see this is a very old thing. It's dated early 60s. So a lot of these special characters are actually control commands for these needle printers that people had at the time. But you also see there's the conventional Latin alphabet in upper and lower case, plus a certain set of punctuation and symbols. I'm sure you're familiar with these. This is what at the beginning of the computer era, everything had to be encoded in ASCII. And so what it does is ASCII simply maps these 128 characters to a 7-bit code word each. So for example, the capital A is mapped to the number 65 in binary, represented by 1, then lots of zeros and another 1 at the end, 5 zeros in the middle. That's a simple mapping back and forth between these symbols and binary strings. That's just enough for the English, for text in English and some other, well, European languages. And that's about it. So the main downside is that this fixed code length is very inflexible. There's no way to add new characters, and there's no easy way to make the alphabet much bigger without increasing the code words substantially. The positive side, though, is because it's so simple, it's as fast as it can possibly be to encode or decode individual characters. And the fact that it's fixed length means we can directly use ASCII to represent a string as an array. Then the array is essentially a long bit array, but I know if I need the 10th character, I just have to jump to bit 70 onwards. So that's why encoding and decoding is fast and allows random access. So that means I can jump to any character right away without doing complicated address manipulations. There's another downside. Unless the characters are roughly equally likely, it wastes a lot of space. And in particular, you see, with the exception of a few of these control commands here are essentially useless today. People included them at the time because they were useful then, and now they've become totally obsolete, but we can't really change the ASCII standard without breaking a lot of existing systems. So these are sticking around and are not used for any good, but they take up space because we have code words that are reserved for this. All right, that's fixed length codes. Let's next look at variable length codes. These are more flexible, but that comes at a price. They're also more complicated. The idea itself is not at all a computer era idea. It's much older, and probably the most well-known is the Morse code. And so here's the international Morse code alphabet. I've learned there's actually different competing ones, so good luck. But SOS is the same in all that I've found, so that's the good thing. And here's a tree representation of the same thing. So if you want to send an A, you have to find it here. So well, this tree here is useful for decoding, right? If you have dot dash, then you know it's an A, and if you have an A, you know here dot dash gives you an A. That's what you have to send. That's for decoding. All right. I suspect people have seen Morse code, or at least played with this a little bit in their free time. If not, it doesn't matter that much. I do want to ask a question about the little nitty-gritty details here, because that is indeed a little tricky. So what is the number of characters in the coded text for the Morse code? And let me go back to just show the code without much additional comment from my side. I just want to give you a second to think about this. And yeah, again, this is not very important for the rest of this module, but it's a good way to practice the terminology and see if you're following this part. So please have your vote on the question. Oh, it's 13 people. We used to have just 25 before. Maybe we can at least get 20. I see 15 votes now, 16, 17. Great. Let me switch back. And I'll show the results when we hit 20. Is that right? 21. Great. Thanks a lot. So here are the results. And interestingly, there's a lot of votes for many of the outcomes. So that probably means we should potentially discuss this a little bit more. Let me state a few facts about this. First of all, there are 26 characters in the Latin alphabet as it is represented here. There are 10 more digits, so that makes a total of 36 characters in the source code, in the source text alphabet, right? So I cannot represent some other punctuation marks, etc. In Morse code, there's just no code for it. But there's 36 different symbols in the source text. Now, I'm representing each and every one of these with dots and dashes. And that sounds like the right answer should be 2, because dot and dash is 2 different outcomes. But the correct answer is 3. Because what's not written here is you actually make a stop, you make a break, a pause between between the individual letters. So if you send A, you do dot, dash, and you make a pause. Because otherwise, how would the decoder know whether you're actually sending an A, so that you have to stop after dot dash, or you're continuing and saying it's an R with dot dash dot? Okay? So the trick here is Morse code really uses a third symbol, which is a blank, to separate individual code words. All right. I think only one person voted for this one. So it was a trick question. I'm a mean guy sometimes. I wanted to trick you into this just to make this very clear. If you have a try like this for decoding, where it's valid to stop and it's valid to continue, that's something where an alarm bell should ring. We'll come back to that as well. Another variable length code that is a little more modern and maybe a little less well known, even though I'm sure you're all using it all of the time, is UTF-8, part of the Unicode standard. So you will know, just as a background, Unicode is the modern way of fixing what ASCII couldn't, namely represent all characters in all languages of mankind, not just the American version and English. And so it contains glyphs and letters for all languages on Earth and a few others like Klingon. And all the emoji, not to forget about those. So, well, as of 2 years ago, it was roughly 138,000. I'm sure there's a few more by now. So that's a large character set. Not 128, but 128,000 and more. So you would need a lot more bits to represent each character in this, but UTF-8 tries to avoid that for the still most common way, still most common type of data, namely English, Latin alphabet text, or codes like on the web, HTML, etc. essentially also use ASCII characters most of the time, with an occasional Unicode smiley in between. So UTF-8 is a smart way to do this while usually saving a lot of space. And what it does is it encodes each character with 1 to 4 bytes, depending on which one it is. ASCII characters use just 1 byte. They start with a 0, and then they have the 7 bits from the old ASCII code that I've shown a couple slides back. Any non-ASCII character starts with 1 to 4 ones in the encoding. This is also shown down here. And that indicates how many bytes in total make up the code for this character. And you terminate this by a 0. So you can either say 0, only 1 byte. You could say 110, 2 bytes, or 1110, 3 bytes, or 4 bytes. And then the follow-up bytes start with a certain pattern to make it obvious when you're reading this byte alone, you know it cannot be an ASCII character. It's actually part of a longer code word. Okay, so this is a smart little trick to help algorithms work in UTF-8 encoded text files. All right, so if you count the axis here, you have a varying length of the actual code for the characters, but it turns out that UTF-8 is enough for the current Unicode character set and a lot of additional new additions that might come. So this seems to combine the best of both worlds. We can, for English text that uses the Latin alphabet most of the time, we get away with 8-bit instead of 7, but that's still pretty good. And still we have the ability to encode all the other Unicode characters as well. Of course, then spending some more space on those. Now, what can go wrong with variable length codes? Maybe one remark here that is in order. If you have a UTF-8 encoded text file, you can no longer easily get random access to it. So maybe for text files, this is not such a big deal. But if you think of a programming language that represents strings, you probably don't want to use UTF-8 as the encoding there, because how could you jump to the 42nd character in the text? Well, you can only jump to the 42nd byte, but how do you know that there's not characters before that that actually used more than 1 byte? So you lose this capability of jumping to a specific character in the text if you use UTF-8. For representing files, it's not usually a big deal. For representing strings in a programming language, it might be a big deal. And languages like Java have found a middle ground. They use UTF-16 and essentially ignore that sometimes the characters need several of these chunks. That's just an aside in case you're wondering about how this could possibly work. What can go wrong in variable length codes? Why do you potentially have to be careful here? So here's a code for characters, and let's encode banana with this. So because we haven't done this before, let's be super explicit about it. I take the first character B, I look up its encoding, I put here its code word 110, and then I just append the next letter. A has code word 0, so I append a 0 for A. N happens to be 10, so I write that. A was a 0, 10 again for N, and another A. That's the coded text for banana in this variable length code. It's obviously variable length because the code words have 1, 2, or 3 bits. Okay, sounds fine. So what could go wrong? The problem is the same coded text, so 11001, it's the same text copied down, also represents another source text. Because you can happily decode as follows. You start with a B, that's so far so good. Then comes an A, that's also good, but then you could read the 100 as an S instead of NA. And that's valid in this code, but it is a problem because we really want to have a lossless compression, so we cannot tolerate this ambiguity here. Now remember, this looks similar to what the Morse code did. So if we added a third symbol that tells us whenever the code word of one character is finished, this would fix the problem. But we don't want to do that because computers are binary, and adding a third possibility for each bit sounds a bit overkill. So Morse code essentially applied a hack to it that works fine in the real world. If you're sending signals over a line, you can add a pause, and that's a reasonable thing to do. It also helps humans as decoders. For computers, we don't want that. So how can we avoid problematic codes like this? We don't really want this. This is a bad code. How can we recognize this? We can recognize it because one code word is a prefix of another code word. And in this case, N, the code word for N is a prefix of the code word for S. And so whenever we read the code word for S, the decoder is left wondering whether it should actually stop at 10 and decode it as an N, or continue and decode it as an S. So the easy fix for this is, and this is what we will essentially always do in this class, we forbid this situation. And it turns out if that situation is forbidden, no other problems are possible. This ambiguity can only arise if we have this one thing is a prefix of something else. So we require the code to be prefix free. No code word is a prefix of another one. And that means we can always instantaneously decode it. If we see in the coded text a code word, and that matches the code word of one character, we know that it has to be the code word for this character, and there's no other chance. So we can parse that, take that as the first character, and continue. So it's a greedy decoding. And that's what we like. That guarantees the unambiguous decoding. Another way to represent this prefix free, if you think back, click, 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 unit 6, we've heard this before. If you take all the code words and represent them in a trie, like so, for this code here, then you immediately see whether or not there is a problem. If all the letters are in leaves, then we're good. There's no code word that's a prefix of another one. If we end up like in the Morse code with internal nodes representing characters, then we have a problem. Then we would either need an end of code word character like in Morse code, or we're in deep trouble. So it's good to think of prefix-free codes, the character codes that we like, as tries. And that's why this has become known as a code trie and has been given this name, because it's used all the time. And you can think of this table that lists the mapping from characters to code words as a convenient way to encode, and the trie is a convenient way to decode. So let's see that on a small example. If we want to encode this here, A is 0, 1. So we use the table to find the code word for A. Then we find the code word for N, 0, 0, 1. And we just append that. Then the space is 3 zeros. Then A is 0, 1, etc., etc. For decoding, the table is inconvenient. You would always have to search in here. The trie is much more convenient, because now you can just walk down the trie reading the coded text. So we do that. The 1 brings us here. The next one brings us here. And then we know, oh, it actually starts with a T. So these two are T. Then we start at the root again. We follow the 1, 0, 0. That leads us to an O. And then we start at the root again, 0, 0, 0. That brings us down here to the space, and so on and so forth. So if you finish this, you find these two codes. So the code trie has two main purposes. It's convenient for decoding. It's an efficient traversal in this trie is an efficient algorithm for decoding. Second cool thing about the trie is it makes it very obvious and explicit if a code is prefix free or not. As a last remark, we've designed character codes, and at this point you have to be a little careful in what exactly is done with this code. And there are three different regimes here. We can either have a fixed code like Morse or UTF-8, where you essentially assume the entire world and everyone who's working with this code knows the code, knows the code trie, knows the table that maps characters to code words. If that is the case, you don't have to transmit the code itself, because it's already known by the other side. A different regime is static coding, where static means that the code stays the same for the entire message that you send, but it's not known a priori. It's constructed based on the source text. So the code depends on the message. So that means you have to transmit it as part of your coded text. Okay. So you would the coded text first begins with a preamble, if you like, that says, what comes now is encoded using this code. And here's the code for the code. We'll actually do this for Huffman. And the third regime is adaptive coding. This is also, you will have to send the code in a sense as part of your coded message. But to make things worse, the code also changes while you encode. So the code is not a fixed thing as in the static case, but it keeps changing. And we'll see with LZW an example of adaptive coding.